Hello and welcome to today's webinar. Today we will be looking at the topic obtaining the best solar yield with Fronius inverters. I would just like to introduce your team for today. I'm Mohammed Sirat. I'm the Technical Sales Advisor for the Southern African region for Fronius. And I am operating from Fronius South Africa, which is an agency of Fronius International. Then I would also like to introduce my colleague, Cyprian Okolo. He is the Technical Sales Advisor for Fronius for Western Africa, and he operates from Fronius International. And then I would like to introduce my colleague, David Mwangi, who is the Technical Sales Advisor for Eastern Africa, and he operates from Fronius International. I would just like to show you the different regions that are supported by your Technical Sales Advisors. So my colleague, David Mwangi, he is responsible for all the Eastern African and Central African countries for Fronius. So as you can see over here. So if you are in one of these countries and you want to contact a Fronius representative, please do get into contact with David. Then my colleague Cyprian, he is responsible for all these West African countries over here. And as I said earlier on, if you are in one of these West African countries and you need assistance on Fronius products, please do contact Cyprian. Then myself, I'm responsible for all these Southern African countries. So again, if you do reside in one of these countries and you would like some Fronius support, please do get into touch with me. I would also like to show you our distributors for the Sub-Saharan African region. Our Fronius distributors are your first point of sales. So they will basically, they stock Fronius inverters and, associated products, which, can be ordered from these distributors over here. They do also offer you aftermarket support. So they are also seen as the first point of service and support. And as you can see in Sub-Saharan Africa, we already have, quite a few distributors, and this ensures that we can really offer you good local support. Okay, just to break down our distributors for some of you that might be new to Fronius, Inomatic Solar and IBC Solar are the distributors for South Africa. Radio Electronic is a distributor for Namibia. One Stop Solar is the distributor for Zimbabwe. Tina Solutions for Ghana. CAT, Green Spark, Knights Energy, and are all the distributors for Kenya. Components and Solutions, that is Nigeria. Sonikara, that is Mali, and then Mother Green Power is Madagascar. Looking at today's agenda, we are going to discuss PV panel optimization. We will then look at maximum power point tracking, after which we'll look at the Dynamic Peak Manager, and we will then conclude with active cooling. Starting off with the first subtopic, which is PV panel optimization. Firstly, what affects DC generation? There are numerous factors that will affect the amount of DC output that your panels will produce. And I'm just listing, let's say, the 8 main effects. Okay, so obviously the first one will be the geographic location. Okay, that's very important. Obviously, the closer you are to the sun belt, the more solar irradiation your panels can, capture. Also looking at your PV panel layout, that also plays a very important factor, which we will be covering in this webinar. Okay, in this webinar, we will also be covering your PV panel orientation, as well as how temperature affects your PV panels. That's another very important factor. Other factors that also affect your DC generation is your time of day, okay, time of year, atmospheric conditions, which again, a lot of installers, sort of don't look at this effect, but this again is very important. Atmospheric conditions could be, anything from cloud cover to, the amount of moisture in the air, etc., that can all, block solar irradiation. Then looking at the last point is your DC cabling. So, due to the time constraints of this webinar, we will only be covering all the red highlighted subtopics, which again is, you can say, one of the main factors that does affect your DC generation. Okay, looking at the first subtopic, this is your PV panel layout. So you get two layouts when you are planning your PV panels, and that is series layout and parallel layouts. Looking at the first one, which is your series layout, the best practice is that you should always have modules in series that should be of the same type of module from the same manufacturer. Okay, that's very important. Never mix panels with different short circuit currents in series. And if you do want more flexibility, you can mix panels with different voltages in series. Okay, so let's say, for example, your distributor doesn't have all of the same panels. You choose to go for all of the panels with the same short circuit currents. But maybe what you could compromise is on the voltages. So your open circuit voltages of the panels. This is in series. Please also note that the performance of a solar array is as strong as the performance of the weakest element. And this is something that we're going to be developing over the next few slides. So looking at your different combinations for a series connection, we're going to look at the first layout over here. Over here, we have three 400-watt panels. Each panel has a open circuit voltage of 40 volts and a short circuit current of 10 amps. So when we add these voltages in series, we obviously get this conclusion. So 40 volts plus 40 volts plus 40 volts gives you 120 volts. Fine. The total current, because it is a series circuit, the total current will be 10 amps. Okay. And the total power, we just take your voltage multiplied by your current, and that's what we can get our total power. What's important to see over here is that the total power has not been degraded due to mixing panels, because we're using all the same panels. And if we add them up, we get that value over there. Looking at the second possibility, which is this possibility over here. As you can see over here, what's happening is that we have two of the same panels, but we have one panel which is a bit different. What is different about this panel? The difference is obviously in the output of open circuit voltage. So this open circuit voltage over here is 20 volts, okay, which is different to these two over here. The short circuit current is still the same, so that's fine. When we add the voltages in series, we get this value of 100 volts. The total current, because it is in series, will be 10 amps. And if you look at the total power of this circuit over here, it will be 1000 watts, which will be equal to the powers of each of these modules added together. So we don't really have any system, underperformance over here. Okay, the issue comes to the point where, as an example, we have this circuit over here where we have three panels, 200 watts, 400 watts, and 400 watts. All of a sudden, over here, we have a short circuit current of 5 amps. Okay, however, our open circuit voltage is still the same. If we look at the total voltage of the circuit, we're going to get 120 volts. We just add the voltages. The current, however, will degrade to the lowest current in the circuit, which in this case will be 5 amps. And because this module is 5 amps, it will affect these other two modules and also the total power output of the system. So over here, all of a sudden, when we do our calculation, we have a total power output of 600 watts, which is less than the individual powers of these panels added together. So if you take 200 watts plus 400, we get 1000 watts, which is greater than the actual power that the circuit is producing, which is 600 watts. So here you can see how the circuit is actually degraded by about 40% because of mismatching, different short circuit currents in series. So we basically will come down to this point for, modules in series. The total current is determined by the panel of the lowest current rating when in series. Okay, we'll now move on to the parallel layouts of your PV modules. The best practice is that all modules in parallel should be of the same type of module from the same manufacturer. Never mix panels with different open circuit voltages in parallel. Okay. If you do want more flexibility, you can mix panels with different currents in parallel. Okay, so here we can see the difference to the series layout. Again, the main statement still stands. The performance of a solar array is as strong as the performance of the weakest elements. So we're now going to look at three different parallel layouts. If you're looking at the first layout over here, we have three 400-watt modules which are in parallel. Okay. Each one has an open circuit voltage of 40 volts and a short circuit current of 10 amps. If you look at the overall voltage of the circuit over here, it will be 40 volts. The total current, because it is a parallel circuit, we just add the currents together, and we get 30 amps. If we look at the total power, it will be 1,200 watts, which is equal to these panels added individually. Okay, so this is allowed. The second combination is when we have 3 panels in parallel. Maybe 2 of the modules are the same and maybe one is different. Okay, the different module will have the same open circuit voltage, but a different short circuit current. And this in turn will lead to a different wattage or different power output. If you look at the total voltage of the circuit, it will be 40 volts. The total current, if we add them together, will be 25 amps. So it's just 5 plus 10 plus 10. If we take the voltage and multiply it by the current, we're left with 1,000 watts, which is equal to all of these panels added individually. So again, this is allowed. If you look at the third option, this is not allowed. You'll see why. Over here, we have 3 panels. 2 of them are the same, one is different. The panel that is different has a different open circuit voltage. So here we can see the open circuit voltage is 20 volts, which is different to 40 volts and 40 volts over here. If you look at the total voltage of this entire circuit, it will be equal to the lowest voltage, okay, which will be 20 volts. So here we can see how the system is really degrading. The total current, okay, because currents in parallel add up, will be 30 amps. And if you look at the total power, multiplying that by that, we get 600 watts, which is less than 1,000 watts. So again, here we can see the system being degraded. Again, so this is not allowed. So this basically leads us to is determined by the panel of the lowest voltage rating when in parallel. Okay, moving on, we will now discuss your PV array design equation. So with this equation over here that I am showing you on the screen, you can use this equation in order to determine how many modules you need to have in series. Okay, in order to make sure that you don't exceed any parameters in your system, such as exceeding the voltage capability of the inverter on the DC side. So if you look at this equation, it's a very simple equation, but basically the main factor over here is N, which is the amount of modules, PV modules. Then we're going to look at these 2 variables over here. So the first one is your V MPPT min. Okay, you might ask, what is V MPPT min? If you refer to the legend over here, it basically stands for the MPPT voltage minimum of the inverter. So this value over here you will get from the data sheet of a Fronius inverter. Okay. Then looking at this second factor over here, which is your MPPT max, if you look at the legend, that basically translates to MPPT voltage maximum of inverter, which again you will get from the data sheet of your Fronius inverter. Then if you look at the second different variable over here, which is your VPM, this basically refers to the working voltage of a PV module, and this you basically get from the data sheet of the PV module. Okay. Then if you look at the next variable, which is T dash, okay, basically what this refers to is your extreme maximum temperature under operating conditions of a PV module. So this factor you will get from the data sheet of the module as well. Then if you look at K-V, basically what that stands for is your temperature coefficient of working voltage of your PV module, which again you will get from the data sheet of your PV module. So if you look at all these variables in red, these are the variables that you will obtain from your data sheet of your Fronius inverter. And all the variables in blue will be the data that you will obtain from the data sheet of your PV module. Okay. And using these variables, we can basically determine how many modules we should have per string. Moving on, we will now have a look at your PV panel orientation. So the general rule is that PV systems in the Northern Hemisphere should have the panels facing true south, and PV systems in the Southern Hemisphere should have their panels facing true geographic north. Okay, remember geographic north is different to magnetic north. So please don't confuse yourself with the 2 different types of north and south that you do get. For the Southern Hemisphere, if more energy is used in the mornings, then the panels should face northeast. If more energy is used in the afternoons, then the panels should face northwest. Okay, so just be aware of, the easterly and westerly orientations of the panels. That will also have an effect in the amount of energy that you want to get at various points in the day. The next point is that the angle that a solar panel should be set at to produce the most energy in a given year is determined by the geographical latitude. Okay. A general rule for optimal annual energy production is to set the solar panel tilt angle equal to the geographical latitude. Let's just take an example. Let's look at Cape Town's coordinates. Okay, so this is Cape Town's coordinates, your latitude value and your longitude value. The latitude is therefore minus 33 degrees. It's a negative value because it's facing south, and hence the ideal tilt angle for panels should be 33 degrees pointing north. Okay, just as an example. Moving on, we will now have a look at the effect of temperature on PV modules. So when the temperature increases, then the short circuit current of a panel also increases. And this represents a proportional relationship. Okay. The next point, when the temperature increases, then the open circuit voltage of a panel decreases. And this is an inversely proportional relationship. Temperature has a greater effect on voltage than what it has on current. Okay, so that is very important. Okay, and you'll also see it in the example that we're going to use over here. So for this example, what I've done is I have taken information from a data sheet of a Canadian Solar CS3W 395 watt panel. Okay. And what I've done is, or what I want to do is I want to determine what would be the short circuit current, the open circuit voltage, and the maximum power production of a 309.
Hello, so I suggest we continue with the next part of the presentation. And when Mohammed is able to sort out the technical issue on his side, then he's going to finish up the part he was explaining towards the end of the webinar. Or are you back, Mo? Okay, so please let's continue and look at maximum power point tracking. So before we do that, I would like to first of all look at what the inverter is doing in the entire mix of your system. And to answer the question, therefore, what does the inverter data say about its capabilities? So when Mohammed was explaining how to sort of calculate the input voltages and stuff like that, in that equation, you saw quite a bit of data that you can get directly from the Fronius inverter datasheet. So in this particular example, we are looking at a Fronius inverter, Echo 27, and what are the production parameters of this inverter as you look at the datasheet. So what the datasheet basically tells us is that the inverter has 1 MPPT embedded. We also look at what is the input maximum current on the DC side. So we see that the inverter can handle up to 47.7 amps. But also the short circuit current is very important when you are designing your array, as well as the fuses for the strings. Also importantly, we consider what is the DC input voltage range. So for the Echo inverter series 27 kilowatt, we see that the inverter can handle anything from 580 to 1,000 volts as far as DC input is concerned. But in terms of the nominal operating voltage, we are looking at 580 volts. Also, the DC connections, the inverter datasheet tells you that, so you can know how many strings you can connect directly to the inverter. So in this case, you can connect up to 6 strings directly to an Echo 27 inverter. Also, in terms of the power handling capacity, you can get this directly from the inverter. So I said this is a 27 kilowatt inverter. And you can see that the maximum PV power that you can connect to this inverter is about 37.8 kilowatts. And therefore, this represents an oversizing capability of 140% if you take the DC to the AC ratio of the inverter. Another inverter that you can look at that is part of an important mix for the commercial installations is the SIMO series of inverters. So in this case, we are looking at the SIMO 10. That means a SIMO or a three-phase 10 kilowatt inverter. And the differentiating factor here is that the inverter has 2 MPPTs embedded. So you can see also in terms of the current input maximum and short circuit current, these are all indicated. What comes as a big difference between the SIMO series and the Echo, for instance, is the fact that the input voltage range for the SIMO series is quite wide. The Echo inverter has a narrower input range from 580 volts to 1000 volts, but the SIMO series is able to take 200 volts up to 1000 volts with a feeding start voltage at 200 volts. So also additionally here, you can connect up to 6 strings, 3 strings per MPPT, just like the Echo series. Although the Echo has 1 MPPT, therefore you connect all the 6 strings to 1 MPPT, but the 6 strings for the SIMO series are divided equally between the 2 MPPTs. In terms of the power handling capacity on the DC side, so you can see that you can connect up to 15 kilowatts on the DC side of the inverter. And if you do the DC-AC ratio, we can see that this inverter is able to do 150% oversizing capability. And these figures I'm talking about because as we are discussing the PV array design, orientation, and so forth, all this power on the DC side is handled by the inverter, and therefore the inverter to a large extent determines how much yield therefore you're going to get out of your PV installation. Before we get into more details on the specific design of the Fronius inverters that allow you to get more yield, I would like also to repeat a section that was covered by my colleague Mohammed and talk about what are the PV production parameters. And most importantly here, I want to highlight the IV curve of the PV module. So as already mentioned, module current is directly proportional to irradiation, and therefore we can see different irradiation conditions here when you have clear sky, cloudy sky, and a very overcast day for that matter. And therefore we can conclude and say that for low irradiation, you're going to get a low current from your PV modules. And for high irradiation, consequently, you're going to get a high current from your PV module. So there are only minimum or minimal changes in voltage levels at different irradiation levels. As a contrast to what my colleague mentioned, so temperature has a huge effect on the PV voltage output, but irradiation variations have minimal effect on voltage levels. So we can see that clearly here. So we start with 1000 watts per meter squared all the way down to 200 watts per meter squared as irradiation conditions that are being encountered by this particular module. And we can see that the variation in terms of the voltage and therefore what is determined as the MPP is a direct effect of the current level at that particular irradiation level and the voltage for that particular light conditions. So what are the main causes, therefore, of yield losses from your PV system? In terms of your PV system, we talk about design-related conditions. We can see a lot of common setup and configuration mistakes. This includes not following the recommended procedures. And yeah, we can talk also about cable sizing, both on the DC and the AC side, as well as how thoroughly this installation is done. We also talk about irradiation levels and variations. We have seen that these irradiation variations are going to have an effect on your current output from your modules. And then we also look at what is the effect of the module orientation on the output of the PV module. Also shading conditions. This could come from both the cloud cover or maybe building superstructures and stuff like that. And also lifetime degradation of your PV array, because as you know, over a period of time, the output from your PV system or PV array is going to reduce as the years progress. So the question therefore is, what happens when the input DC voltage is not optimal? So the voltage that you're feeding to your PV inverter. So all Fronius Snap inverters except the Eco series will have a booster circuit in them. So this is something that is going to boost the voltage up. So the Eco series, as we saw, has a narrower input voltage, although this is quite high, from 580 to 1000 volts. So it means that therefore for it to operate, it does not need to be the voltage to be boosted. But the SIMO series, for instance, we saw that the input voltage is quite wide, from 200 volts up to 1000 volts. And therefore, it means that when you have the input volts at maybe 300 volts, and the optimal MPP point for the inverter is something like 580 volts thereabout, it means that the inverter must have a mechanism inside to boost this voltage from 300 up to a voltage that will ensure that the inverter is giving you the right output on the AC side. So therefore, to maintain efficiency of the inverter, the booster circuit is switched on or off depending on the threshold of the DC input from the PV array, as we can see here. So from 300 up to 595, for instance, the booster is switched on. But if the input voltage on the DC side is above 595 all the way up to 800, then the booster circuit in the inverter is off. So let's now look at the specific features of the Fronius inverter that are going to allow you to get a lot more yield compared to other inverters in the market. And one of the things that we can talk about is the Superflex design. And I would like to explain to you what this Superflex design is. So some of the few things that we can note down are that some inverters have a main and a secondary input. So if you have an inverter, for instance, with 2 MPPTs, you would find that one inverter takes about 80% of the input, and then MPPT B or MPPT2, which would be the secondary input, is designed to take only 20% of the rated inverter handling power capacity. Other inverters are designed with equal inputs, so the primary and the secondary inputs can handle 50% of the power that can be connected to the inverter. And therefore, MPPT1 in this case would take 50% of the power, and MPPT2 is going to take 50% of the remaining power. And therefore, the inverter in this case will have no MPPT taking more than 50% of the connected DC power. So the Fronius Superflex design combines the two variations in one design or in one inverter. And therefore, whether for MPPT A or B, you can have either more power on MPPT A or MPPT B without a problem. You can also have unsymmetric distribution, e.g. in cases of shading, you can have MPPT A taking 80% of the connected power, and MPPT 2 is taking only 20% of the connected power. In other cases or other variations, when you have symmetric distribution, so that you have equal modules on each of the orientations, you can have a 75% share of the power connected to MPPT A and a 75% of the power connected to B. And in this case, if you combine or you multiply 75% times 2, we are talking about an inverter that has been oversized by a factor of 150%. So what does the Superflex design therefore address? So Superflex design is going to address modules that have different orientations, as we can see here. It's also going to address asymmetric PV installation spaces. So if you have a roof like this, as we're going to see next, and you have a typical commercial roof space, on one side it could be east or west, and maybe on one side of the roof, you're not able to put a big number of modules than the other, then that is an asymmetric distribution of the modules. So in most cases for typical commercial roof spaces, you find that the modules will be installed facing one direction. For instance, for this design over here, we could have all the modules facing east or west, depending on the location or the geographical conditions. And then also we have another variation whereby it's possible that you have 2 or 3 orientations depending on the roof complexity. So you can see that in the next picture over here, we have modules that are oriented in 3 different orientations. So you have one that is facing east and west, another one facing the southern direction. So in this particular case, you have a lot of variations depending on the time of the day on how much PV power, therefore, is going to be delivered to the inverter. So when you have these kind of conditions, especially where the orientations become quite complex, we do recommend that you do a combination of different Fronius inverters. So for instance, you can have a combination between two SIMO inverters with 2 MPPTs, and also an echo inverter with 1 MPPT. So the echo will take all the modules that are oriented in one direction, and then the SIMO, because it's quite flexible with 2 MPPTs, is going to take the section of the roof and the array that are oriented in different directions, and therefore that is going to limit the degradation of power that is being fed to the inverter depending on the time of the day, because each MPPT in the SIMO is able to treat each orientation as a separate installation, but within the inverter they are combined to give you the same output. So you can also have greater flexibility, for instance, when using our newer commercial inverters such as the Tauro 50 kilowatt, because this inverter already has 3 MPPTs. So for this kind of complex roof where you have 3 different orientations of the PV array, the Tauro on its own is able to take care of each orientation and treat it as one system within the inverter when the changing of DC to AC is happening. This therefore also begs the question, how many MPPTs therefore are ideal in an inverter for design flexibility? We have seen a lot of inverters in the market that are talking about having even 12 MPPTs in one inverter. So this is a discussion that we can have in a different training. But of course, there are pros and cons of having so many MPPTs in one inverter. And also look at, can one MPPT or 2 MPPTs in one inverter do an equally good job as an inverter that has so many embedded MPPTs? So going on, let's look at the Dynamic Peak Manager and how this is going to assist you to get more yield from your PV system. So the Dynamic Peak Manager is embedded as a standard in all Fronius inverters. And what it does basically is to locate the best maximum power point at each input voltage. So it doesn't matter whether irradiation conditions are changing, the Dynamic Peak Manager is checking always for the best operating point as well as far as maximum power point is concerned. And therefore, this allows faster adoption to changing irradiation levels. And the algorithm is going to scan the PV array curve entirely every 5 minutes or so. And once it finds a new maximum power point, then it compares with the previous maximum power point to check which one has more power, and therefore feed the most DC power from whichever power point, maximum power point has more power after the calibrations. So the Dynamic Peak Manager can be accessed, of course, if you want to switch it off. This is an option that is provided by Fronius, so you can switch it on or off, but the default setting is on when you get the inverter from the factory. So this can be accessed through the basic service menu of the Fronius inverter. Therefore, what we want also to highlight as we go to the next slides is that the Dynamic Peak Manager is a highly efficient shadow tolerant algorithm, and this is going to help you to get a lot more yield from your PV system regardless of partial shading conditions. So how do you then maximize your yield at the shade? As we have seen, the maximum power point of a PV module is the point at which you get most power out of the IV curve. And the maximum power point is tracking is a technique, therefore, to extract the most from your PV modules under all conditions. So there is an algorithm already inbuilt into the inverter, and most inverters already have this, that is going to scan the IV curve from time to time to find the best operating point, as we can see in this IV diagram. However, there are problems with the normal MPPTs, because in most cases, a normal MPPT is going to scan only a section of the IV curve and is going to be stuck in what we refer to as the local maximum power point. So in this IV curve diagram over here, we can see that we have two different maximum power points. We have what we are referring to here as the local maximum power point, and we also have a global maximum power point. So in this case, if the MPPT does not have something as intelligent as the Dynamic Peak Manager from Fronius, is going to operate at the local maximum power point, because every time the MPPT is shifting the operating voltage up and down, it realizes that the output power is going down and therefore runs back to the local maximum power point. In contrast, however, we can look at what the Fronius Dynamic Peak Manager is doing. And to do this, we are going to be using a specific working example. And we are going to analyze a system that is about 3.3 kilowatt peak with a southwest orientation and a tilt angle of 19.5 degrees with partial shading. So we can see that during some time of the day, there's a bit of shade that is cast on the modules for a particular section of the morning. So, and this is the period from 8:45 a.m. to 10 a.m. And we are looking here, therefore, at what would be the production curve of the inverter without the dynamic peak manager. So we can see that from 8:45 to 10 a.m., we are missing quite a bit of power that we can get, as we can see here, shaded in gray and red. But if you bring the dynamic peak manager into the picture, as I said, this is already integrated as standard in the Fronius inverter. Instead of getting stuck in the local maximum power point, the dynamic peak manager is going to allow the inverter to scan the entire IV curve, and it's therefore going to compare both maximum power points, both the local maximum power point and the global maximum power point, and therefore establish at which point the inverter is going to produce most power and feed DC power, or allow the inverter to operate at that particular point. So looking at this particular example, we can see that with the green area here, we can see what is the added or additional production or yield with the dynamic peak manager integrated. And therefore, if you compare over the entire production curve during the day, we can see that this is about 7% more yield with the dynamic peak manager. If you were to look at exactly a bigger system, and therefore look at a 300 kilowatt peak system that is exposed to good irradiation levels for about 6 hours per day, we can see this 7% more yield would be equivalent to about 126 kilowatt hours per day. And annually, if you consider maybe 9.5 good months of irradiation, we can say that the dynamic peak manager, compared to an inverter that is operating without a dynamic peak manager, is going to guarantee you more yield of about 35,900 kilowatt hours. And over the life of the system, this would come up to about 0.9 megawatt hours. If you look at the cost of power, and if you are in a scenario whereby you want to use as much power as you're generating from your PV system, or you are selling to the grid if this is allowed in your region, then you can talk about what is the saving or the earnings that the dynamic peak manager has given you over the life of the system, which is approximately 25 years. And in this case, we can see that because of the dynamic peak manager integrated in the Fronius inverter, you can be guaranteed $179,000 more savings or earnings over the life of the system. And therefore, what we can say is that the bigger the system, the more the yields that you're going to get out of the Fronius inverter. So that basically brings me to the end of my section. But before I hand over to my colleague, Cyprian, I would like to launch a poll, and I would appreciate if all of you could kindly share your feedback with us on this question. So the question is, how do you do your installations with different or how often do you do installations with varying orientations? That is, if you are faced with instances whereby your modules are oriented in different directions for a particular installation. So kindly share your feedback with us on this. And I'll be leaving the poll question on for the next 20 seconds or so, and then I'll close it and share the results with you. So thank you for all of you who have been able to share your feedback on this. So just about 5 seconds more, then I close it. All right, so I close it, and then I'll share the feedback with you. So from the feedback, we can see that the biggest portion of attendees today say that they do installations with the orientations of PV array, different orientations quite often at 41%. At that 1% say they rarely do it, and then 16% they say they never do with different orientations, and 13% they say they do it all the time. So the same question I asked before applies. So how many MPPTs would you think is ideal or would be ideal in one inverter to guarantee you maximum yield based on the different orientations? And what kind of technology can allow Superflex design or flexible design of your PV installation? So I think, as already covered in this content today, we can see that Fronius allows you to seamlessly integrate different inverter models, a SIMO combined with an Echo, or even the Tauro inverter combined with the snap inverters, to guarantee that regardless of the kind of orientations that you're facing, you can still generate maximum yield out of your PV installation. So at this point, I would like to hand over to my colleague, Cyprian, to continue with the remaining bit of the presentation. So Cyprian, please take over from here.
Okay, thanks a lot, David, for a wonderful presentation. But yeah, Mo is back on now, so he will continue with the rest of his part of the presentation. So Mo, you can continue.
Thank you, Cyprian. Yes, just apologies for that short disconnection I had in my presentation early on. But basically, to pick up where we left off, we were looking at the effect of temperature on PV cells. And just to recap, for those who were not present in the earlier part of today's webinar, basically what happens when temperature increases, then your short circuit current of your panel also increases. And this is represented as a proportional relationship. When the temperature increases, then the open circuit voltage of a panel decreases, and this is an inversely proportional relationship. What's important to note is that temperature has a greater effect on voltage than what it does have on current. Okay, so what I basically did was I had a look at a Canadian Solar CS3W 395 watt datasheet, and I basically pulled out these values from that datasheet. Okay, so what I'm going to do is I'm going to show you how temperature really affects a PV module by using an example. So in today's example, the question is, what would be the short circuit current, open circuit voltage, and maximum power production of a 395 watt panel at 50 degrees Celsius? Okay, so what's important to note is that when we refer to the data sheet of a solar module, it will always give you the quoted values under standard testing conditions. So what is standard testing conditions? Standard testing conditions is done at an irradiation level of 1000 watts per meter squared, a spectrum of 1.5, which is your air mass, and your cell temperature of 25 degrees Celsius. So basically that is your standard testing conditions. And it also happens to be the optimal operating conditions for a PV module. So looking back at the question, we can basically, look at these important parameters. So at your standard testing conditions, your short circuit current will be 10.82 amps. We get it from year over year. Then at 25 degrees Celsius, your open circuit voltage will be 47 volts, which we get from the data sheet. And your maximum power production will be 395 watts, which we get from the data sheet. Your temperature coefficient for current we also get from the data sheet, and that will be 0.05% per degrees Celsius. Your temperature coefficient for voltage we also get from the data sheet, and that will be negative 0.28% per degree Celsius. And your temperature coefficient for your power we also get from the data sheet, and in this case it will be negative 0.36% per degree Celsius. Okay, so here we can clearly see that with an increase in temperature, your power is affected the most, which is then followed by your voltage in a negative way. However, temperature will positively affect your current, but in a very small manner. So in effect, your voltage effect actually outrules the current effect, which basically leads to a degradation in power output whenever your temperature increases. So let's look at the question again. So what would be the short circuit current at 50 degrees Celsius? Basically, the equation you will use will always stay the same. You basically take your standard condition, okay, of your short circuit current, which will be your short circuit current at 25 degrees Celsius, and you then multiply it by 1 plus your temperature coefficient of current multiplied by the change in temperature over 100. So when we plug in these values into this calculation over here, we then get this over here. As you can see, for the change in temperature, it's your 50 degrees minus your standard operating conditions, which is 25 degrees. When we plug all of that into the calculation, we can then see at 50 degrees Celsius, our short circuit current will be 10.96 amps, which is actually bigger than what it was at 25 degrees Celsius. Okay. We then do the exact same thing for the voltage. However, please note for the voltage, it has its own voltage coefficient. And when we obviously plug it into the equation, we then get left with 43.71 volts. So here we can see how the voltage is actually affected in a negative way. So the initial voltage was 47 volts. Now at 50 degrees Celsius, we now have a degraded voltage of 43.71 volts. We then do the exact same thing for your maximum power production. The only difference in the equation here is your power coefficient, okay, which in this case will be negative 0.36, and obviously your variable in the front. When you plug all of that into the equation, we then get left with 359 watts. So here you can see at 50 degrees Celsius, we actually have quite a system degradation, all from 395 watts all the way to 359 watts. And this is why it's very important to always look at the effect of temperature whenever you are, planning a PV system. Moving on, we'll now look at the next factor that will affect your DC generation, which will obviously be your DC cabling. So with DC cabling sizing, the general rules is that the current carrying capacity must be equal to or greater than the current to be carried. Okay, and this is on your DC side. Okay, so basically from your DC generation on your PV panels. A good suggestion is to always size for 1.25 times the nominal current of the system. And you must always be able to withstand environmental conditions. Please also pay special attention to the voltage drop, which basically increases with cable length. So the longer the cable, the more voltage drop you will have. Consideration has to be placed on whether the cable is stranded or solid core. Okay. So I think in this picture over here, I've shown you, the difference. You get, solid core over here, and then you also get stranded as well. The next point to pay attention to is the specific conductance of the cable has to be considered. So your specific conductance of copper, for example, is 58 times 10 to the power of 6 Siemens per meter. Okay, and this is a alternative indication of the same notation over here. For aluminium, it's slightly lower. So here we can see copper has a better conductance than aluminium. However, as most of you already do know, aluminium is a bit cheaper than copper. So it's especially a trade-off that you always need to look at on your DC cabling. For example, aluminium has a conductance of around about 36, times 10 to the power of 6 Siemens per meter. What you then need to do as a PV design engineer is that you sort of need to figure out what is an acceptable loss in the system that you will accept as a designing engineer. And you basically decide on a factor. So let's say you maybe, for example, decide that you only want a 1 or 2% loss. And that will also determine what your sizings will be for the system. But if you look at the power loss equation, so that is indicated by P loss is equal to I squared R. Okay, so how do we get R? We get R from taking 1 over your conductance, okay? And you multiply that by the length over the area of the cable. Okay, so this length over here is the length of from the panel to the inverter. And obviously the area is your cross-sectional area of the cable that you are looking at. Okay, when you plug all of this into the equation, you get your resistance value, okay? And you then multiply that by the square of the expected current outputs of the panels. And you can then determine your power loss. Okay, so again, this is very variable and it can be dependent on what the design engineer will decide is an acceptable power loss. Okay, so for example, in this system over here, I wanted a 1% acceptable loss with a 1000-volt DC system, which was producing 10 amps, and the length of the cable run was 20 meters. When I calculated this in the equation, I was basically, going for a 1.5 millimeter squared cable, and that obviously translated to a 16 AWG cable size. Okay, before I hand over to my colleague Cyprian, I would just like to launch a quick poll. I'll just really appreciate if everybody could share their answers. The question is, what method would you use to ensure optimal and economical cooling of solar panels installed in high temperature conditions? Okay, the first option is float the PV modules on water. And as you know, that's generally called floating PV. The second option is elevate the PV modules from ground. So you're basically providing air cooling for your PV modules. The third option is to use thin foam PV panels, which is different to the conventional, poly and monocrystalline modules. So with thin film PV panels, you get a much better performance at higher temperatures, at an increase of about 30% compared to normal panels. And then your fourth option is automated water spray system. So yes, please do select one of those following options. I will keep this question open for the next 30 seconds. Okay, I will now be closing the poll. Thank you, everybody who shared their answers. Okay, just to share the results with today's attendees, we can see that the majority of today's attendees actually prefer, elevating the modules from ground level, and that is probably due to cost. Okay, which is then followed up by automated water spray system, which is then followed by using thin film PV panels. So for example, I can see a reason why nobody chose the first option. Obviously floating PV is very expensive to, go about actually installing. I'd like to hand over to my colleague Cyprian, who will take you through the last part of the presentation. Cyprian?
Okay, Mo, thanks a lot for concluding your part. We'll be continuing with the conclusive part of this presentation. I'd like to crave your indulgence, all the attendees, for a bit of patience. I know that we've kind of extended the usual time we take for the presentation. Okay, so we'll be continuing with the active cooling technology. Sorry, I believe we can now see my screen. Great. I hadn't turned it on initially. Great. So in view of the topic has been discussed, how to obtain higher yield for Fronius PV systems, we tend to look at how the active cooling brings about better yield for your system. So if you now ask what is the concept of active cooling and why is it a better technology for power electronics, we'll start off by defining what active cooling means, which is basically cooling or proactively avoiding heat fields using strategically located interior fans, and of course to remove warm air in a controlled manner. So just by definition. So at Fronius, active cooling is a technology standard in all our devices. So in addition to a heat sink that is located, of course, inside the inverter, there is a fan to ensure that the air inside inverters is circulating and so-called hotspots are avoided. Another fan is also responsible for keeping the cooling pins of the power electronics at low temperature. The fan speed tends to vary, subject to the temperature inside the device. So basically, we have fans strategically situated in our snap inverters, for example, up and down. And then this is for the snap inverters, but I must also say that for our newly designed Gen 24 inverters, it also employs active cooling, but in this case has a larger centralized fan that does both function, both circulating the air and then, of course, cooling the power electronics to avoid hotspots by centrally absorbing cool air and then radially dissipating heat across the inverter. Good. So just to emphasize more on it, active cooling usually employs 2 fans, except for the Gen 24 Plus, as earlier described. One for cooling the heat sink and then one for internal circulation of air, as we can see illustrated in this example over here. And as against passive cooling, which is usually employed by some of our competitors. In this case, they depend, or this system depends on cooling by convection. Usually there are no fans, but some improvement. Some tend to have a fan installed inside, but then the main means of cooling the system is by convection. And as you can see, hotspots are easily generated in these systems. And then, of course, you can see from the temperature difference, we have more than 10 degrees Celsius temperature difference for these systems. So having said that, we'll now take a brief look at the advantages of active cooling. So to start with, of course, it makes the system cost less because there will be almost no maintenance needed, and which leads to low maintenance costs. Of course, in relation to the topic of discussion today, you would have more yield because you'll have better performance with more yield, and then save cooling technology that guarantees highest yield for your system. Of course, it makes it easy because the inverter has less weight, and then makes it for easy installation in case where you have multiple installations, so long as the procedures and the clearance gaps are met. So, of course, it also leads to flexibility in mounting of the inverter regarding the mounting location because of our active cooling technology. And at the end of the day, it leads to a longer lifespan of the power electronics due to lower temperature of the inverter components that have been maintained because of the use of this technology. So looking at another advantage, you have more flexibility for mounting, as I've earlier stated in the bullet, the previous slide. With this mean that it makes for flexibility in terms of orientation of the installation. So for systems that are not actively cooled or that depends on passive cooling, you cannot have such installations. It will have to be a vertically upward installation for it to attain some sort of degree of cooling. So yeah, so this is the reason why actively cooled Fronius devices makes it pretty easy for you to install. So of course, it gets longer lifetime for devices because the longer or the hotter electronic parts gets, the shorter the lifespan of the power electronics. And this has been proven by an experiment that was carried out. And this experiment postulated that for every increased 10 degrees Celsius increase of temperature, it sort of halves the lifetime of electronics or power electronics. So this is very critical, which is why at Fronius we make it a very serious point of call to ensure that our systems are actively cooled so that there will be less stress on the electrical components, thereby ensuring a longer lifetime. So if an inverter is exposed to high temperatures, of course, the output power will be reduced. And then, of course, this has a negative impact on the yield. Thereby, you have lesser yield with higher temperatures. This is because of derating, which we will be discussing, of course, subsequently. So inverters with active cooling technology have better power derating behavior because of the cooling effect that is much more effective and stronger. And this can be seen from this illustration. Tests carried out between Fronius and a tier 1 competitor, and both implementing different cooling technology. So for Fronius, like earlier said, implement active cooling technology, and passive cooling is the method employed by this competitor. And we can see the results. The blue colored graph is that of the competitor, while the red colored graph is that of the Fronius. And at different voltage levels, we can see that the Fronius way outperforms the competitor by far in terms of derating. Okay, so now let's look at the impact. So the previous slide was sort of a chart. We'll now look at a live situation. So this is actually an existing system. It's a 90 kilowatt peak installation. This system consists of 4 SIMO-20s and 1 SIMO-10, making it 90 kilowatt installation on a 99.84 kilowatts peak PV system or installation. So as we can see in this case, these are live and real data. We can see that even at very high ambient temperatures, even more than 50 degrees centigrade ambient temperature, you have still optimal performance from our Fronius device. So you will now ask the question, if an inverter that was passively cooled was used in this case, this would be the situation, because at these temperature limits or at this temperature point, the derating will definitely set in, and eventually you would have this power curve, meaning that you would have a significant loss if the active with passive cooling, that is, if active cooling was not employed. So as we can see, yes, so as we can see, we would have had significant loss if passive cooling was employed. And by calculation, it was calculated that out of 674 kilowatt hour energy generated, the calculated loss that would have occurred if passive cooling was implemented would be 96 kilowatt hour, which amounts to approximately 15% of the entire energy generated, which is quite high in terms of power loss. Okay, so with active cooling, you have less maintenance, less or even no maintenance. So active cooling is usually maintenance free, and of course, which give rise to low cost. But otherwise, there will be need for dust to be constantly removed in short intervals, sometimes every 6 months. And this is proven here by a checklist that was drawn from a tier 1 competitor. So as we can see in this case, as highlighted here, it is stipulated in this routine maintenance checklist that dust will have to be cleaned off this device twice a year. So this, of course, implies high maintenance costs, because you'd have to visit the site and then carry out these maintenance processes, especially in areas of particularly dusty regions or locations. So conclusively, we're going to look at the Fronius active cooling fans, looking at some particular myth or claim. And yeah, so there has been a session that the Fronius device or inverters cannot achieve IP66 if our fans or if our inverters have fans. But then in reality, our fans or the fans used in Fronius inverters are sealed internally and have a rating of up to IP67. So which means that the fan can operate even underwater temporarily. And then the fans have high protection class than the entire inverter. So this, of course, debunks this myth or claim. And buttressing more on it, the data beside, as you can see, shows the real operating data from 2 devices exposed to extremely high temperatures over a 1-year period. The hours of fan operation are categorized according to 5 ambient temperature categories, ranges in steps of 10 degrees Celsius, as we can see, 20 to 30, 30 to 40, 40 to 50, 50 to 60, and 60 to 70. Now, from the analysis obtained from this data, the design of the speed control fans in Fronius active cooling system devices is such that they only run at full speed if the ambient temperature reaches 60 degrees. So, but in practice, this operating point, as shown from the graphs, as you can see, only occurs for a few hours a year. The fans, therefore, runs at lower speed for the remaining operating time in the year. And as you can see, there are, this was actually carried out for 3 countries, and taking Australia, for example, which is a very, very hot, usually have very hot season or summers, we can see that in a particular, the fan hardly or doesn't even run at a high speed, as you can see in this case. So it doesn't reach 60 degrees Celsius, as we can see. So with this, it shows that the design for or the use of actively cooling technology employed by Fronius is, of course, the best technology that would guarantee high yield for our PV systems. And of course, with a service life of more than 20 years, it of course gives you more assuredness of better service. So that brings me to the end of my part of the presentation. But for further information, we have available on our homepage operating and installation instructions on our YouTube channel. You can get how-to and installation videos, webinar recordings, and then specifically speaking, if you are looking for a playlist of all our webinars that have been presented over time, you can actually access it via this link. So it contains a compendium of all the webinars we've presented, so for easy reference purposes. And then your Fronius team that you can always contact for inquiries, for technical cases, trainings, after sales, and of course sales. And then particularly speaking, and as Mohammed has earlier said, you can reach us with respect to our covered regions. So that has been the presentation for today. Thanks once again for your patience. It was indeed a pleasure. We will take some time, maybe 2 or 3 minutes, to look at some questions you've sent using the chat function, and then provide the answers to them eventually. So until next week, when we will be coming your way with a fresh and interesting topic, I'm wishing you a wonderful weekend. Thank you all.